Right. So section 3.3, which is now covering rates of change and behavior of graphs. We have four objectives in this section. Being able to find the average rate of change of a function. Sort of want to think of slope, your change in y over change in x. The reason why it's called an average rate of change is we're not just dealing with linear functions now, we're dealing with cubics, quartics, piecewise functions. And so when we find the average rate of change, we find it between 2 points on the graph. And then we take the difference between those two y values and divide it between the difference between those two x values. So from a formulaic perspective, we're looking at the difference between our two y values in function notation, f of b minus f of a, all over b minus a, which is essentially your change in y over your change in x, but it's not linear, or it doesn't have to be linear. Our second objective is being able to use a graph to determine where a function is increasing, decreasing, or is constant. Constant is horizontal lines, or just horizontal. Third objective, being able to locate local maximum and local minimum. So peaks of graphs, or like the top of a hump or the bottom of a dip. And then the last objective is locating absolute maximum and absolute minimums, also known as global max and global mins. That's a synonym, where it's the lowest value of the graph or the highest value of the graph. Sometimes you won't have an absolute min, and that's the case when you have arrows shooting up to infinity because there is no maximum. And vice versa, if you have arrows shooting down, you'll have no absolute minimum because it will be shooting to negative infinity. I started recording, right? Yeah. Just want to double check. Okay. So let's jump into our first objective for this section, which is the average rate of change. And I know I wrote it out earlier on the previous slide. And I used B and A. That's the most common notation used in a lot of textbooks, but on the slides here, we're using X1 and X2. I'm just going to write it with the B and A here as well. Even on like SAT exams, which you don't have to take, but if you end up graduating and you want a master's degree or you go for your PhD, you'll have to take the GREs, or if you end up become a doctor, GMATs, which involves some mathematics. Average rate of change does pop up on those standardized exams, and most cases you have or are given those B and A variables. And again, it's the difference between your y over the difference between your x. So let's jump into our first example where we're asked to find the average rate of change along this interval. Whenever they give you the interval, that's the indication of what your A and your B values are. This is your A and this is your B. You're always reading it from left to right. So essentially, when you're finding your average rate of change, you're finding the difference between your f of a and f of b all over b minus a. So what is f of 2 minus f of a over your b is 2 minus your a is -1? Two negatives gives you a positive. So we're looking at f of 2 minus f of negative 1 all over 3. Should have wrote this as negative 1. You're probably asking yourself, well, what is f of 2? Or what is f of negative 1? That's where the graph comes into play. Because your f of 2, you just want to find where x is 2 and then figure out what is that y value. X is 2, your y is 1. And when your x is negative 1, your y is also 1. Nope, that was wrong. X is negative 1, goes up here. Your y is 4. So substitute that in, and you end up with 1 minus 4 all over 3. That's negative 3 over 3, which gives you negative 1. That's your answer. Right. Any questions on this problem? I'll maybe color code this part as well. So you know where these values come from. And I think it should be f of 2 minus f of negative 1. I wrote this incorrectly up here. Right, example 2, this time we're going to compute average rate of change from a table perspective. And this whole paragraph tells you, okay, what is our A and what's our B value? So after picking up a friend who lives 10 miles away and leaving on a trip, Anna records her distance from home over time. The values are shown in the table below, and we want to find her average speed over the first 6 hours. So that's the key. First 6 hours, which means our A is going to be from the start, which is 0, and then our B is up until that 6-hour marker. And then we just plug it in, f of B minus f of A all over B minus A. Our f of B is 292. F of A is 10. All over 6 minus 0. So we get 282 all over 6. And that is what? 4 goes into, I'm just going to do it off to the side here because I cannot think right now. Yeah, thank you. Yep, beautiful. And it's her average speed, so 47 miles per hour. Don't want to forget the units when we're done. Right? Another average rate problem. Again, we're given now a function. We once again have our a and b values. So we're essentially finding f of 4 minus f of 2 all over 4 minus 2. Evaluate what f of 4 is. Wherever you see an x, put in parentheses, and then fill in those parentheses with 4. And then you do the same thing for f of 2. Four squared is 16, minus 1/4. 2 squared is 4, minus 1/2. 4 as a fraction is just 8 over 2. So you get 8 minus 1 over 2, which is 7 over 2. 16 as a fraction is 64 over 4 minus 1 over 4. So 64 minus 1 over 4 gives you 63 over 4. And so now we're looking at 63 over 4 minus 7 over 2. But 7 over 2 is the same as 14 over 4. So we get those same denominators. All over 4 minus 2, which is just 2. So that numerator can be simplified a little bit. 63 minus 14 gives you 49, right? So we have 49 over 4 divided by 2 over 1, keep, change, flip. And essentially we're looking at 49 over 8 is your solution. You can keep it in improper fraction form, or you can convert it into a mixed fraction. How many times does 8 go into 49? It goes in 6 times, remainder 1. So if you wanted to say 6 1/8, that would work as well. A lot of just computing, but the hardest part is just knowing your average rate of change formula and just substituting it in. Questions at all? No. Okay. Let's keep going. Another average rate of change example, where now we're dealing with a quadratic as our function, but again, it's really knowing what your a and your b values are here. This might be a little confusing because our b ends up being our variable a. Don't have that trip you up. So we're looking at f of a minus f of 0 all over a minus 0. And so we want to plug in a wherever we see a t. So we have a squared plus 3a plus 1 minus, and then plug in 0 wherever we see a t. 0 squared plus 3 times 0, which is just 0, plus 1, all over a minus 0 is just a. And then just simplify at this point. First one can't be simplified quite yet. And then these will all shoot to 0, and then you'll be left with 1. So minus 1 all over a. That helps us out because 1 minus 1 cancels out. And then a squared plus 3a, we can factor out an a. So we have a in parentheses, a plus 3 all over a. which will cancel out the a in the numerator and the a in the denominator, since a divided by a is 1. And so our final simplified result is just a plus 3 as our average rate of change. And then we're done. How do you guys feel on this question? Scale of 1 to 5. 5 being good. Okay. Again, I'd say if you're 3 or lower, really try to watch this section of the video again. And if it helps, you can like star it in your notebook and say section 3.3, example 4. I'd say we're about 20 minutes into the video. So maybe put in parentheses about 20 minutes in. Right. The second objective, this part is fun because at least at this phase right now in calculus, you'll be able to determine increasing and decreasing from a technical standpoint, just looking at the function itself. But at our level right now, we're determining it very visually, looking at the graphs. And so if you see it increasing from left to right, then that's your increasing range. If you see it decreasing, it's going downhill, that's your decreasing range. If you see nothing happening and it's at that horizontal line, then you obviously have it as constant at that area or at that point. And so, yeah, this is a fun section that we'll get to practice together with. So our example 5 is we're just finding intervals on which the function is increasing. So again, read the graph left to right. Where is your uphill? Obviously, we know that this is all downhill. This is a constant, right? That's your tipping point from it going decreasing to an uphill, which is increasing. So we have our first interval of increasing is from 1 up until 3. And then you'll notice that it's downhill again, and then we have another increase. From, we'll just call that 4 up into infinity since we have that arrow. So our intervals of increasing are from -1 to 3, union, and then 4 to infinity. You can also write, instead of union, you can write and. And sometimes you can also write just a comma between the two intervals. So there's just all different ways of writing it. Right. Now we're on to our third objective where we identify local maxima and minima. And you'll see here we have one local max and one local min, but sometimes we'll be dealing with parabolas that have multiple humps. And so both of these, in this particular example, are local maxes, whereas we have two local mins as well. So you can have more than one local max and local min. You cannot have more than one absolute max and absolute min, because the absolute tells us that, okay, what's the absolute value that hits that maximum in the function or hits that minimum in the function. And up here is just the formalized notes from a technical standpoint with identifying what is a local max and local min. And you do it based off of increasing and decreasing. You know your local max is going to be wedged between an increasing and a decreasing part. That creates that hump. Whereas a local min is going to be wedged between a decreasing and then an increasing, because that's going to represent where that dip takes place. So now knowing that, let's tackle example 6 together, where we're asked to find all the local max and local min. Because we're dealing with a cubic function here, we don't have many local max and local min. In fact, we have one of each. This orange one is what? A min or a max? Yeah, we have a local min here. And our local min is always, sometimes people like to identify it by the coordinate point, but if you're asked on an exam, like what the global min, global max, local min, local max are, it's usually identified by the Y value. So local min at Y is, or in this case, F is equal to -2. And then you could put in parentheses when X is equal to -1, but that's not necessary. The more important part is identifying it at that Y value. Whereas your Y coordinate, or not your Y coordinate, your local max is going to be at +2. Two. And then in parentheses, we can write when X is equal to 1. That's it. Yeah.
So the only important point was to be Y.
Yeah. It's good to know the coordinate point, but like when you write it on an exam, write it in Y form. You can write it as f of x equals -2 or f of x equals 2. But you could also write it as y equals -2, y equals 2. Do it in the notation they ask, because sometimes they'll have h of p or g of x. Then you want to say g of x is equal to 2. All right. And then this is just a slide based off of the toolkit functions for increasing and decreasing intervals. Again, you don't have to memorize any of this. If you know the constant function, you can see that it's not going to be increasing or decreasing. Whereas if you're looking at a linear function, you know that it's always going to be increasing unless the slope is negative and it's going in the other direction. And then from a quadratic form, when we're dealing with parabolas, you know that you're going to have different intervals. It's going to be decreasing at first and then increasing. Cubic function again, just look at the visuals and you'll very easily be able to identify what's happening. And then we have more of our toolkit functions. Mathematics is very, very visual. If you know the graphs, you can really find loads of information just by looking at it. The domain, the range, intervals of increasing, intervals of decreasing, your end behaviors, which we'll be looking at in a moment. And now we're on to our objective 4, where we're going to be finding our absolute maxes and our absolute mins. And this paragraph is just stating the differences between local mins and local maxes versus absolute mins and absolute maxes. Again, if you were dealing with, and I'll give you maybe a visual example. Let's say we had that defeated the whole purpose. Try it one more time. Maybe I just need a little less bumps. Okay. And this one here is just going to be slightly, no, actually we don't need it to be, because this one's the lowest. So we clearly have a local min right here. We have one here. We have one here. Do we have an absolute min? Where? Right here? Is that an absolute min?
No, because the range.
Yeah, it shoots down to what?
Negative.
Yeah, so no absolute min. Okay, let's look at some local maxes. Is this guy a local max? It's not. It's only a local max if it has that sort of top of the peak visual. This just stops. There's no peak. So we don't have that decreasing that takes place. What about an absolute max? Yeah.
Right.
I'll label them, yeah. Yeah, exactly. We have an absolute max here. This absolute max, is it also a local max? Yeah. So there are cases where you can have an absolute max be the same as a local max, but not all local max are absolute maxes. These are local maxes, but they're not absolute. This is both absolute and local. Whereas from the mins, these are all local mins. None of these are absolute because it shoots down to negative infinity. So we actually have no absolute here. We only have local mins. Does that make sense? Yeah. And so this paragraph essentially talks about the differences between local maxes and mins versus absolute maxes and mins, and how you can have an absolute max or an absolute min that is also local, but it doesn't always have to be the case. And so this is, this is another thing that I want to say. Even though this is not a local max, because it's not in that sort of peak format or dip format, if we're talking about mins, when we're dealing with absolute mins and maxes, you don't have to have a peak. Like this, if this was lower and this was the highest point, so let's say this went up to here, then this would be your absolute max. Absolute just essentially says what is your highest or minimum value of the function. And so on this slide, this is just another example of how to find your absolute maximums and minimums. You're just looking for your highest or your lowest value on the graph. And then these are just formal definitions. Again, you don't have to have that increasing, decreasing, or that decreasing, increasing, aka the little dips or the peaks when you're dealing with the absolute maxes and mins. You're just looking at either the highest possible value that your function hits at that y coordinate level versus your lowest possible value. So now let's take a look at example 7 and tackle this together. We just want to find all the absolute max and mins. And again, it's absolute, so you're really only going to have one solution in both cases. So what is our absolute max here? You said 16? Yeah, good. And both of these cases, it's 16. Yeah, so, and it's F, so F is equal to 16. And then what about our absolute min? Are you sure? Remember, absolute, you just look at the smallest value of the whole function. Yeah, yeah. Good. Any questions on this one? All right. So that concludes our section 3.3. And then our next section is 3.4, which is dealing with composition of functions.